Hello, welcome back to A-level online chemistry, specifically part 2 of mass spectrometry and how to solve problems involving isotopic abundance. We have looked at how mass spectrometers are built and how they work, and in this part 2 we're going to look at some questions that might be asked in an exam context and how these might be solved. Before we start, let us define atomic mass units. Right. Atomic mass units, or Daltons, the vast majority of chemists around the world use the UPAC convention, which stands for International Union of Pure and Applied Chemistry. They actually have a very good website with some interesting things on it, which states that 1 Dalton equals 1/12 of the mass of 1 atom of carbon-12. So most elemental samples that you'll get here on Earth consist of a mixture of different isotopes. They're the pure element, but there's maybe 2 or 3 different isotopes in that element, and they exist in varying proportions. This makes calculation of the relative atomic mass sample more complex, so it needs to be like an average of all of the isotopes and how much of those isotopes there are in the sample. So the relative isotopic mass is defined as the mass on atom of the isotope divided by 1/12, 1/12 of 1 atom of carbon-12. The relative atomic mass, that's got the symbol A subscript R, then becomes the weight averaged mass of the relative isotopic masses of the element. So that's the sample of the element that we're looking at. Incidentally, on Dalton, like 1 atomic mass unit equals 1.661, to 4 significant figures, times 10 to the minus 27 kilograms. A mass spectrometer takes measurements in m/z, which we can read as atomic mass units on a properly calibrated machine. So mass units, mu or u, and these are equal to Daltons. They're exactly the same. So calculating relative atomic mass from a mass spectrum. Relative atomic mass from a mass spectrum. I'm going to quickly sketch a mass spectrum here. And this is going to be a mass spectrum of neon. And in the spectrum we get 3 peaks, with intensities of 114, 0.2 and 11.2. This is m/z. So this is ms of neon, a sample of neon. We need to take each isotopic mass and multiply it by its abundance in the spectrum, or the relative abundance in percentage or as a fraction, it doesn't matter which, and then we sum these up. AR equals 114 times 20 plus 0.2 times 21 plus 11.2 times 22. So these are the abundances with the little a's above them, and these are the masses with the little m's. And we divide these by the sum of the abundances. So we're then going to add the a's together at the bottom, so it's 114 plus 2 plus 11.2. This gives the weight average atomic mass of the sample. And if we do this sum, come to an answer of 20.18. Now we're only going to quote it to 1 decimal place. So AR equals 20.2, which is weight averaged atomic mass of a sample of neon. The raw information might be given to you in a number of forms, for example in a table, perhaps with percentage abundances or fractional abundances. The process is the same. I'm just going to draw a quick table to show you. I'll just use the information from the example that we've just done involving neon. So let's just m/z and abundance. So 20, 21, 22, it's 114, 0.2, 11.2. So it could be given to you like that. There's a variation of this question which can be a little tricky if you can't just work it out in your head. And I will go through this now. So the question is, for example, if a boron sample has an atomic mass of 10.8, so AR equals, if this sample gives a mass spec with two peaks, one at 10 and one at m over z equals 11, what is the ratio of the heights of the two peaks? So look, it's the same sum. We can say 108, which is the AR, 10.8, which is the AR, equals, but we need to basically substitute something in there to represent the abundances. So it's going to be 10 times x plus 11 times y. And that would be over x plus y. Now, if we think about this, because we've got two peaks, if we know what x is, we know what y is. Like there's only two things in it. And if x plus y equals 1, then y must equal 1 minus x. So we can say 10.8 10x plus 1 minus x, which equals 10x, and let's expand out that bracket, plus 11x, which equals 0.2 minus 0.2 equals 1x. So therefore x equals 0.2, and therefore y equals 1 minus 0.2, which is 0.8. So the ratio is 0.2 to 0.8. So B11 0.8 to 0.2 E10, which equals 4 to 1. Let's make sure that's B11 E10. I've selected some examples of questions from previous exam papers and collated these into exercise 1.3. Now would be a good time to go through these. So in these two videos, we've covered how a spectrometer works, and two, we've looked at some exam style questions regarding isotopic abundance and mass spectrometry. So this is the end of this lecture. So thank you for listening.